All right, Chapter 11, Section 2, Series. All right, what do we mean when we express a number as an infinite decimal? For instance, what does it mean to write pi, which is 3.14? And I know normally we just stop there as a pretty good approximation at 3.14, but it does go on, obviously. It's an irrational number. It goes on forever, and there's no way to express it as a rational fraction. And the digits never repeat themselves, right? There's never an established pattern as we go on. But okay, so we can take this decimal, this infinite decimal, and rewrite it in terms of an addition of fractions, right? So this is how your author rewrote it, but let me just expand on that a little bit. So we have the 3.14. So what we could do is we could say that that's just equal to 3. Whoops. We could say that that's just equal to 3. And then to that, we're going to add 0.1. And then to that, we're going to add 0.04. And then to that, we're going to add 0.001. And then to that, we're going to add 0.0005. Right? So you see where I'm going with this. And then the next one's a 9. And then 0.00000. And the next one's a 2. 0.0000006. Okay, you can see where we're heading with this, right? So dot, 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 keep going in this way. And so if I wanted to do this summation, the way we would do it is, going back to old school adding of decimals, what we would do is add the missing zeros, right? Right? If we wanted to add these as they are right now, then we would add down, and well, there's nothing below the 3, so that just comes down as a 3. And then the decimal, and then there's a 0 there, and there's a 1, and then everything below the 1 is 0, so it's just going to become a 1. And then 0, 0, and then there's a 4, and nothing below the 4 but 0, so that's where the 4 comes in. And then it's all zeros, and then a 1, and nothing below the 1 but zeros, so we put a 1 there. Then all zeros, then a 5, then all zeros, so we put a 5 there. All zeros, then a 9, so we put a 9 there, and then a 2, and then a 6, right? So that's where we begin the process of writing down the first few decimals. So we want to use this process to represent this, right? Except I stopped at the 6. We want to keep going this way. So let me erase this for a minute. Say, okay, we don't want to stop there. We want to keep going. I can see the process is working. And now what happens is that we get to rewrite each one of these as a fraction. So if we do that, right? So this one is just going to be 3. Okay. And then 0.1, well, that's just equal to 1/10. And then 0.04, that's in the hundredths place. So that's going to be equal to plus 4 over 100, right? That takes care of this one. Let me put it in color. So this one goes there, and then this one is that one, and then this one is that one, and then the next one is going to be 1 over 1,000 plus 1 over 1,000 plus the next one is 5 over 10,000. Oops. 5 over 10,000 plus the one after that is going to be 9 over 100,000. And so on and so forth, so on and so forth, right? So that's the pattern. And now, instead of writing 10, 100, 1,000, 10,000, we can rewrite them in terms of powers of 10. Right, let me continue to point these out. That one was that one. That one is that one. That one is that one. And then, we would continue. So I'm just going to rewrite each one of these now as the following. It's 3 plus 1 over 10 plus 4 over 10 squared, that's 100, plus 1 over 10 to the third power, that's 1,000, plus 5 over 10 to the fourth power, that's 10,000, plus 9 over 10 to the fifth power, plus dot, 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 dot. Okay, and we keep going forever, and if we keep going forever, eventually we can represent that infinite decimal, right? So that's where this came from. So I was just expanding on where your author came up with this, right? Each one of these values in the numerator of the fraction is the digits of pi, and the denominator is growing by powers of 10, right? So this is one way to represent this. Pi can be written this way as well. And of course, this goes on forever. We never stop, right? This only expresses it out to 6.5, out to this decimal place here. But the little dots indicate that we keep going in that pattern. Okay, so this is a very common way in math in which we can represent a decimal into a fraction. A summation of fractions. And that's what we're going to be working with in this section. So, in general, if we try to add the terms of an infinite sequence, a sub n, out to infinity, we get an expression of this form. A sub 1 plus a sub 2 plus a sub 3. Remember that the actual values, a sub 1, a sub 2, is a sequence. Right, so we could have, from the previous section, we saw that a sequence is just a list of numbers, right? It could be something that has a pattern like 3, 9, 27, 81, dot, 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 right? So this could be my sequence, where this is the first one in my sequence, so that's a sub 1, a sub 2, a sub 3, a sub 4. So here's a sequence, and there's a very obvious pattern. It could be a sequence that doesn't have a very obvious pattern, like 0, 2, negative 1, 2, 3, 7, negative 1. Like, what is happening? Is there a pattern? Is there no pattern? What's happening here? Well, okay, it's worth investigating. Maybe there is some really cool pattern that helps you predict what the next value is going to be on the list, or maybe there is no pattern. Either way, when we just have the list of values, that's called a sequence. Okay, so it's the first one on my list, the second one on my list, the third one on my list, the fourth one on my list, so on and so forth. Okay, but now if we're interested in adding these values, now it turns into a series. Okay, an infinite series is the sum of the values of an infinite sequence. Okay. So a sub 1, a sub 2, a sub 3, that's a sequence, right? And then when we add them together, that turns into an infinite series or just a series. And we denote it in this fashion. The sum from n goes from 1 to infinity of a sub n, or just very often, I think it's kind of lazy, we probably shouldn't do this, but we often don't include the limits of the sum, and so it's just kind of assumed that they're there. But I don't like assumptions. People make mistakes when they have assumptions like that, but it's pretty common. Okay, so remember that this means that we keep adding all of these. We replace the n with 1, then 2, then 3, then 4, and we don't stop until we get to this value. And since it's infinity, it just means we don't stop. We just keep going on forever. So this equals that. Okay, so it would be impossible to find an actual sum of a sequence in certain cases. For example, it would be impossible to find the finite sum of this series, right? If it goes 1, 2, 3, 4, 5, 6, 7, 8, right? It just keeps going on that along that way. This is a an example where the sequence a sub n is just equal to n, right? The first one on my list, a sub 1, it's 1. The second one on my list, a sub 2, it's 2. The third one on my list, it's 3, right? Very simple pattern. Okay, so now if I want to add all of these, I would have to add a sub 1 plus a sub 2 plus a sub 3 plus dot 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 dot. So that amounts to adding 1 plus 2 plus 3 plus dot 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 dot. Okay, and that's what this is representing. 1, 2, 3, 4, 5, 6, dot 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 dot, all the way out to n and then beyond, right? We don't want to stop at n, we want to keep going. And so this would be impossible to get a finite sum to all of this, because if we start adding up the terms, the cumulative sums, 1, then 3, then 6, then 10, and so on and so forth, and after the nth term, we get n times n plus 1 over 2. Okay, so let's see where that comes from. Okay, so let's go off to the side and do a little proof by induction to see where that comes from. So hopefully you've seen this before. If not, it's a great little practice, right? So let's say we want to do this. Show that the sum of the first n numbers show that 1 plus 2 plus 3 plus dot 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 out to n is equal to n times n plus 1 over 2. We're going to do proof by induction. Okay, so if you recall, step number 1 is to show it works for n equals to 1. Show the formula works, n equals to 1 works. Okay, so n equals to 1 means that on the left-hand side, we're just going to have the 1. Show that 1 equals 2, and then on the right-hand side, that if we replace n with 1, that we get a true statement. So we'll have the 1 from there, and then parentheses plus 1 divided by 2, and then we get another 1 over here. Okay, and that makes sense, right? We end up with 1 plus 1 is 2, divided by 2 is 1, so 1 equals 1, and so we get a true statement. It works. Okay, then next in the proof by induction process is just assume it works for n. Assume that 1 plus 2 plus 3 plus dot 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 all the way out to n does in fact equal to n plus 1 over, you know what, let's change it a little bit. Assume it works for n equals to k. Let's just change it up a little bit. Assume it works for n equal to k. So let me erase this. Too close there. N equals to k, some kth value, assume that it works up to there. So let's spell out what that means. 1 plus 2 plus 3 plus dot 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 all the way out to k, right? Some value way out there, assume it works for there. So therefore that'll be equal to, this will be equal to divided by 2 parentheses plus 1, and then we'll have a k here and then a k plus 1 over 2. So assume that's true. And then the important part in the proof by induction is the third part here is now show it works for the next one, for n equal to k plus 1. K plus 1. Good? Okay, so that means that we want to show that 1 plus 2 plus 3 plus dot 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 dot. And then way out here we have the k. And then right next to it we have the one that comes next, which is going to be the k plus 1. Show that this whole thing is equal to, and then plugging into my formula, I have a 2 there, a blank plus 1, and then I have a k plus 1 that goes in here, and then a k plus 1 that comes out here, right? That's just replacing a k plus 1 into my formula, this formula. All right, let me make that smaller. Okay, so the key to this then is to realize that we want to show that it goes all the way out to k plus 1, but the one right before it was k. Therefore, all of this from there all the way up to there is this one, right? So then we get to insert k times k plus 1 divided by 2, k plus 1 divided by 2, and then there's still a k plus 1 out here, k plus 1 plus that is equal to this, right? That's what we're trying to show. So we still have a k plus 1, and then there's a k plus 1 here, and then plus 1, and then the whole thing divided by 2. Good? Okay, so now I'm going to multiply the numerator and denominator of this fraction by a 2, get everything underneath with a 2. Or likewise, I could multiply everything by 2. I feel like I'll do that instead. So I'm going to multiply everything on this side by a 2, distribute, and then multiply this side by a 2. And let's repeat that over here. So what happens? When I distribute, this 2 cancels, so I'll just be left with a k times a k plus 1 plus, and now this 2 multiplies a k plus 1 equals, and then on the right hand side those 2 cancel, so I'll be left with this, which would be k plus 1 times k plus 1 plus 1. Good. Okay, so now let's simplify. Distributing, I get a k squared plus k plus 2k plus 2 equals to k plus 1 times k plus 2. Good. And then we get to combine some like terms. This turns into k squared plus 3k plus 2 equals to k plus 1 times k plus 2. And if we factor or FOIL, either way, let's just factor this. This is k plus 1 times k plus 2 equals to k plus 1 times k plus 2. Right? If we FOIL this, we get k squared plus 2k plus k gets us to 3k plus 2. And so we've established that the left-hand side equals the right-hand side. Therefore, this is true. Right? We've shown that, kind of reversed here, this is true for any value of k, right? Because they're identical. Therefore, this must be true, because all I did was FOIL it, which therefore that means that this is true. Okay, I just scrambled it a little bit. That must be true. Okay, which means that this must be true, right? All we do is regroup some of these things, expand it, which means that this must be true, which means that this must be true. And so we've established that by induction that this is true. So by the induction process, we can conclude that 1 plus 2 plus 3 plus ... out to n must be equal to n times n plus 1 over 2. Okay, that was just a little side detour. So we've established that that's true. Okay, now going back to here, going back to where we were, we want to work with this infinite sum. It doesn't stop anywhere, but we do have a formula for the first n values. So if we add the very first one, obviously it's a 1. The sum of the first two, right, if I add up the first two, they add up to 3. That's this number right here. Good. And then if I add up the first 3, that's going to be 6. That's this one right there. Then if I add up the first 4, they add up to 10. That's this number right there. Good. And so on and so forth. And so if I add up the first n of these numbers, they add up to this guy. Right? We just proved that. Okay, but now if we keep looking at that sum and we consider this thing, right? Think about what happens as n gets larger and larger and larger, right? After the nth term, we get this, which becomes very large as n increases, right? So this is hopefully pointing out that this infinite sum is not going to add up to any constant. It's just going to keep getting bigger and bigger and bigger. It's going to diverge. It's going to go off to infinity. Okay. On the other hand, what if we had this sequence? Consider this one. We have 1/2, I'm sorry, this series, right? The sum is a series. 1/2, 1/4, 1/8, 1/16, 1/32, so on and so forth, so on and so forth, right? This one is your classic pi scenario, which I'm sure all of you guys have heard. We have one whole pi, one entire pi. And so the very first day, you decide, you know what, I'm going to cut this up and I'm only going to eat half of it. Day 1, right? Day one, we eat half my pie. Okay, day number 2, you come back and you know what, I'm going to eat half of the half I have left over. So I take half of my half is a fourth. So on day number 2, you eat a fourth. That's this guy. Good. Then the next day, you eat half of what you have left over, which was 1/4, and half of a fourth is 1/8. So on day 3, you have 1/8, and that's this part, right? And then, let's get another color going in here. On day, let's go with purple. On day 4, you have 1/8 left over, so you eat half of that. That's going to get you to 1/16. So that's this one. And that's going to be day 4. You have 1/16. Okay, that's what this is. So if you start adding up how much of the pie you've eaten, right? Day 1, you ate a half. Day 2, you ate a fourth, so if you add them together, you get 1/2 plus 1/4, right? Just the first 2 days. 1/2 plus 1/4, common denominator is a 2. So we gotta multiply this by 2 over 2. We end up with 3/4. 3/4. That's what this is, 3/4. Okay, and then what about after the third day? If we add up the first 3 of them, okay, well that's gonna be equal to 1/2 plus 1/4 plus 1/8. Common denominator is going to be equal to 2 over 2 and 4 over 4. So that'll be 8 and 2, I'm sorry, 4 and 2 makes it 6, 7 over 8. 7 over 8. And that's what this is, 7 over 8. The sum of the first day, then the sum of the first 2 days, then the first 3 days, then the first 4 days, right? And so this is the pattern we start to see as we move forward. Good. And we want to see what happens if we add up all of these days forever, right? On the one hand, it seems a little counterintuitive, I think, that if we have a sum that goes on forever, that it ever adds up to anything, right? So if I'm just staring at this and I go, keep adding all these fractions forever, what are they going to add up to? It might seem a little counterintuitive. But if we look at this pi scenario, right, 1/4, then a fourth, then an eighth, then a 16th, so on and so forth. Even though it's going to be a process that goes on forever, it makes sense that the whole thing is just one pi, right? If I lead in this process forever, at forever, I've eaten 1 pie. If I ever stop anywhere before forever, then I wouldn't have eaten the complete pie. I might get really close to eating the pie, right? If I continue this process for 10 days, 20 days, 100 days, I will eventually eat the majority of the pie, almost all of it. But if I ever stop before infinity, there will always be, mathematically at least, a tiny little sliver left over, right? We can always just cut that in half, cut it in half, cut it in half, cut it in half. In reality, physics stops us at some point, right? You can't go on cutting it in half forever, but in math we can. So if we go on forever, we have 1 pie. If we ever stop before forever, we don't quite have it. We get really close. We can get infinitely close to 1, but not quite there. Okay? All right, so that's what's happening here. We're just going to start adding these up forever. We notice that the pattern is right here at the nth one. These are powers of a half. 1/2, 1/4, 1/8, right? Looking at denominators, 2, 4, 8, 16. These are powers of 2. So the nth term, the nth day, this is how much you would be eating. Good. And if we start adding them up, sort of the running sum, day 1 and day 2 together is 3/4. Day 1, 2, and 3 together, it's 7/8. Then 15, 16ths, and so on and so forth. And you can see the pattern that's emerging from here as we keep going. This last one should have been this is a mistake, sorry. There should be a little comma here, not a plus. Whoops. There should be a comma. Okay, anyway, so we can see what's happening. And then we get to this formula. This formula represents the sum of the first n values. I will revisit this in a little bit, see where this came from. But for now, let's just assume that that's true. This little formula tells you the sum of the first n numbers. And we can see from here what the pattern is. In case you don't, we can further see that by converting all of these things into decimals. So let's see this table here. This table does this. It adds up the first, it shows the summation of all of these, the first n values. Okay, so let's repeat that. Let's recreate this table here. Let's use that. All right, let's just use our calculator to recreate this table a little bit here. Good practice. I'm going to go to Stat, Edit. I'm going to clear list 1, clear it, and clear list 2, clear it, clear. Okay, so for list 1, I'm just going to put in the values of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's just do the first 10. Okay, so now the actual values of my sequence, let's go up here to L2 and create a little formula. And L2 is going to be equal to 1 divided by, and then I'll put it in parentheses, 2 to the power of, and I want it to be one of these values. So I'm going to put L1 right there. Move it to the right, close the parentheses, hit enter, and there we go. So this creates all of those fractional values that are in my sequence. These guys. Right? 0.5 is a half, and 0.25 is a fourth, and 0.125, that's 1/8, and 0.0625, that's 1/16, then 1/32nd, then 1/64th, and so on and so forth, so on and so forth. Okay, so now let's use the formula that they gave us here. Again, we'll come back to revisit this in a little bit and see where this came from. So let's go over to list 3 and highlight L3. And I'm going to put in this formula here, but instead of n, I'm going to choose L1. So this will be equal to 1 minus, and then in parentheses, I'm going to put 0.5. 0.5 to the power of, and then L1. Good. Enter. And let's just confirm that it makes sense. So the first one is just the sum of the first one. Yeah, that's just 0.75. The second one is the sum of the first two. 0.75 plus 0.25, that adds up to 0.75. And now 0.25, 0.5 times plus 0.25 plus 0.125, that adds up to 0.875. And then the sum of the first four adds up to this one, and the sum of the first five adds up to that one, and so on and so forth. Okay, so that's how I can recreate this table on my calculator. I can also visually see it on Desmos. So let's see if I can use Desmos. So let's graph, oops. Desmos. Let's see, we have y equals to, no. Table. Just make it n. And we have 1 divided by 2 to the n power. 1, 2. Here's the first 10 of them. Okay, so these are the values in my sequence. Let's make this a little more, we're in projector mode. So here's the first 10 of them. Okay, so that point is 1 comma 1/2. That point is 2 comma 0.25. Next one is 3 comma 1.25, and so on and so forth, so on and so forth. Okay, so here's the first 10 values in my sequence. And now if I want to add them, that was the next one over here, and that one is 1 minus 0.5. Again, we'll revisit where this formula comes from in a little bit, to the power of n. And here they are. So 0.5, 0.5, then the sum of the first two, 0.75. Sum of the next one, that's this one, and sum of that one, that one, so on, that one, and that one. Okay, so we can see that this is sort of the running sum of the first n values equals to this. And you can see that Desmos has already graphed it. So this one is both green and purple, and it just represents the same dot. Right? It's the first number on my sequence. It's also the first number in my series, in my partial. The sum of the first one on my list. Okay, and you can see that it is growing, but it's bounded, right? And it's growing toward the line y equals 1. Right? It's getting infinitely close to that value. Good. So I think that that's, visually we can see that's a pretty good guess as to where it's going. Now it looks like it's arrived here, but remember that's a deception. If we zoom in to these guys, zoom in, zoom in, zoom in, zoom in, zoom in, eventually we see that in fact there's a little gap there. The purple one is not on the red one. The purple one, the dots, are getting close to that horizontal line at y equals to 1, but they're never going to be quite there. Right? So the graph is a little deceptive. It kind of looks like the dot is on the red one, but it's not. It's just getting infinitely close to it. Okay, so we're getting really, really close to the line y equals to 1. Good. Okay, so let's go back over here. So here's our table. The table shows that as we add more and more terms, we see that it begins to grow closer and closer and closer to 1. That's a good indication of where it's going, but that's not a proof yet. So we haven't proven that that's true. We're just getting ourselves familiar with the series and maybe have like a pretty good idea of what the answer should be based on this. Okay. All right, so in fact, by adding sufficiently many terms to the series, we can make partial sums as close to 1 as possible, right? So if we just add the first 10 of these, the first 20 of these, we get really close. If someone says, I'll believe you when you're 0.0000000000001 away from 1, that's when I'll believe you. Okay, no problem. All I have to do is figure out how far down this list to go, and eventually I'll be able to find a number such that if I, let's say a number k down here, such that if I add up the first k of them on my sequence, that sum will be close enough to 1 to meet any threshold that someone might throw. Okay, so it seems reasonable to say that the sum of the infinite series is 1, and to write that this is true, right? That the sum, as n goes from 1 to infinity of 1 over 2 to the nth power, which is equal to this, dot, 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 equals 1. We use a similar idea to determine whether or not a general series has a sum. So consider the following, we call these partial sums. Consider the following partial sums. This is going to be based on a sequence, right? We have a sequence, a sub 1, a sub 2. We have a sequence. What is happening? Oh, why do I have a marker? We have a sequence A1, A2, A3, right? This is a sequence, dot, 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 dot. And now we're interested in the series. What happens when we add these? 1 plus A sub 2 plus A sub 3 plus dot, 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 as we add them. Okay, so then we consider these partial sums. S sub 1 is going to be the sum of the first one on my list. S sub 2 is the sum of the first 2 on my list. Then S sub 3 is the sum of the first 3, the sum of the first 4, and you get the point. So eventually we come up with this new sequence of values where each one of them is a partial sum of the first n values. Good? So if we extend this out to the nth one, it'll be this, the sum of the first n values. Good? These partial sums form a new sequence, S sub n, which may or may not have a limit, right? Okay, so we are interested in figuring out if the partial sums head towards somewhere, if they have a limit themselves. So if the limit as n goes to infinity of S sub n equals to some s, the notation is a little weird here, so pay attention to the fact that here we have an n, S sub n, so this is partial sums, and then equals some s with no sub n, right? Just the letter s, right? So this represents a value such that if the limit as n goes to infinity of S sub n equals to s exists and is a finite number, then as in the preceding example, we call it the sum. We call it the sum of the infinite series, right? So this is then equal to the value s. Right? So by definition, given a series, which is going to be equal to this, from 1 to infinity of a sub n equals a sub 1 plus a sub 2 plus a sub 3, dot, 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 so on and so forth, we can let S sub n denote the nth partial sums, right? The sum of the first n of them, if the sequence of partial sums is convergent and the limit as n goes to infinity of S sub n equals to s exists as a real number, so it converges and it has the limit as n goes to infinity of S sub n equals to s, then the original series that we were interested in is called convergent, and we can rewrite it by saying that this is in fact equal to s. Good. The sum is called the sum of partial sums. Good. Okay, thus the sum of a series is the limit of the sequence of partial sums. So when we write that the sum from 1 to infinity of a sub n equals to s, we mean that by adding sufficiently many terms of the series, we can get as close to as we'd like to the number s. right? Notice that this is equal to this. So here we stop at n and then apply a limit. The limit as n goes to infinity of the sum of a sub I as I goes from 1 to n is the same thing as this notation. Okay? All right, so now armed with all this new knowledge, let's get back to this one and reapply all this new notation and ideas. So remember the sequence. Let's just review some of this stuff. So the sequence is 1/2, comma, 1/4, comma, 1/8, comma, dot, 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 dot. Another way to refer to the sequence is to say that it's a sub n equals to 1/2 to the nth power, right? This generates these values in my sequence. Okay, so now I'm interested in the series, and the series is this one. It's what happens when you add these up forever. Plus 1/4, plus 1/8, right? Plus 1/16, plus dot, 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 forever. Somewhere out there is the 1/2 to the nth power, but then it keeps going, right? We want to go on forever. So one way to do this is to think of the partial sums. So we have s sub 1, the sum of the first one on my list. Well, that's just going to be 1/2. Okay? And then s sub 2, well, that's going to be 1/2 plus 1/4. Common denominator of 2/2. Let's put a common denominator here of 2/2 gets me to 3/4. 3/4. Okay, and then s sub 3, that's going to be 1/2 plus 1/4 plus 1/8. Common denominator in this case is equal to 8, so let's put a 2/2 there and a 4/4 there, which gives me 4 plus 2 makes it 6, 7/8, 7/8. Okay, all right, we start to see a pattern. Maybe let's do one more. So s sub 4 is going to be equal to 1/2 plus 1/4 plus 1/8 plus 1/16. Common denominator in this case is going to be 16. So it'll be 2/2 there and 4/4 there and 8/8 there. And they add up to 8 plus 4 is 12, 14, 15/16. 15/16. Okay, at this point, let's look at some patterns here. Notice that in every single case, we have a fraction, right? The sum of the first values adds up to a fraction where the denominator is powers of 2, right? 2, 4, 8, 16. My money is that the next one, right? I don't even have to do it all. My money is that if I do the next one, it's going to add up to some fraction where we have a 32 in the denominator, right? Because it's got powers of 2. 2, 4, 8. And also, if I want to rewrite it as powers of 2, notice that, okay, that's just 2. And this is going to be 3/2 squared. And this one is going to be equal to 15/2 to the third power. And this one, I suspect, is going to have something to do with that, right? And notice that the relationship between these guys, wait, what did I do? I missed one. And this one is 2 to the third, 7/2 to the third. And this one is 15/2 to the fourth. And this one, I'm guessing, is going to be 2 to the fifth. And notice the relationship between this. This is s sub 1, the first one on my list, and it's 2 to the power of 1. And this one is s sub 2, the sum of the first two, and this has 2 to the second power. And then the sum of the first 3, and this is 2 to the third power. And this is the sum of the first 4, and this is 2 to the fourth power. sum of the first 5, and this is 2 to the 5th power, right? So if I kept going and said, well, what about the sum of the first n of these, s sub n? Well, again, I think it would be a pretty good guess that this is going to be 2 to the power of n. Just noticing that pattern, that this one always matches the power of 2 in the denominator. And then one more thing, the numerator is always 1 less. This is a 2, this is a 1. This is a 4, this is a 3. This is an 8, this is a 7. So it's just equal to the same thing, minus 1. Right? So this one is going to be 32 minus 1, or just 31. 31. Good. And if we wanted to write it in terms of this, I can write it as 2 to the 5th minus 1. Right? That'll be 32 minus 1 is 31. So going out to the nth one, this is equal to 2 to the nth minus 1. The sum of the first n numbers. Good? Good, good, good. Okay, so that's what we get here. We get that s sub n. Let's put it back over here. So the sum of the first n numbers sum of the first n values in the sequence, in the series, 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot 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 dot. Okay, the sum of the first n of them, that's the partial sum, is equal to 2 to the nth minus 1 over 2 to the nth, which can be simplified as 2 to the nth over 2 to the n, 2 to the n, minus 1 over 2 to the n, and then these simplify, so s sub n is equal to 1 minus 1 over 2 to the n, the sum of the first n of these. Okay, and that's where this formula came from. I know we've been using it a little bit. Let's come back up here. That's where this came from up here. 1 minus 1/2 to the nth power. This is the same thing. 1 minus 1 over 2 to the n is the same thing as 1 minus 1/2 to the power of n, right? We can do like a distribution of exponents here, and 1 to the nth power is always 1. So these two things equal each other. And that's where this formula came from. There. Okay, and so what happens as we think about taking that out forever? What's going to happen as we let the limit of this go to infinity? So now, the limit as n goes to infinity as f sub n, right, this guy is going to be equal to the limit as n goes to infinity of 1 minus 1 over 2 to the n. And so this guy, it's parentheses, this guy will go towards 0. So the whole thing will approach 1. Good. So that's why we can show that this whole thing adds up to 1. Good. So we were using this part here. We found the s sub n value, right? We showed that that part, when we do the limit as n goes to infinity, that thing converges to 1. So the 1 is the s here in our little example for us. In our little example for us, the s was the 1. We showed that the limit of our partial sum as n goes to infinity equals to 1, and so we were able to conclude that the original series also equals to 1. All right, let's move on to another example. Another important example of an infinite series is something called the geometric series, very commonly used. A geometric series is a series that happens to have a pattern like this. This is where a equals to some constant not equal to 0. If it was equal to 0, if a was allowed to be 0, then this would be a very simple series. Every single term would multiply a times r, which equals 0. So every individual term would be 0, and they would all add up to 0. So clearly, we want to only consider cases where a doesn't equal to 0. Okay, so r. What can r be? R can be a variety of things. So let's consider what happens for a couple of different situations. If r equals to 1, another really simple thing happens here. If r equals to 1, then this is a 1, and this is a 1, and this is a 1. Anything 1 raised to the power of any integer value is always going to be 1. So we just end up with a sum of a's. A plus 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 a. So s sub n, the first of the sum of the first n of these is going to be equal to n times a. Good. And the limit as n goes to infinity, the limit as n goes to infinity of n times a, where a is not 0, a is some number. Well, if a is positive, well, then the whole thing goes off to positive infinity. And if a is negative, well, then the whole thing goes off to negative infinity. Right? Either way, it just blows up, right? It just keeps growing forever and ever and ever. So this is the limit as n goes to infinity of s sub n. What we've shown here is that the partial sums diverge. The limit as n goes to infinity of s sub n does not exist, and so therefore the geometric series diverges. Right? This is when r equals to 1, exactly 1. The whole thing diverges. All right, well, now let's consider something else. What if r does not equal to 1? If r does not equal to 1, right, in all other cases, r doesn't equal to 1, let's do this right here. Okay, so what is that? Let me expand on that a little bit. We want to find the sum of the first n values, right? So s sub n equals to a, it's the first term, and then ar, and then ar squared, and then dot, 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 dot. And then we're going to stop at ar to the n minus 1. Notice that we can also kind of complete this pattern by writing a 0 here. I can also do a r to the 0 power. R to the 0 power is a 1, right? And then this is a 1 there, and a 2 and a 3. Okay, so this kind of goes by, you can kind of look at the terms by powers by the exponents, 0, 1, 2, 3. So this is the first term on my list, and this is my second term on my list, and this is my third term on my list, da 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 da. So notice how the exponent is always 1 smaller than the index, its value on the sequence. That's why once we get to a sub n, the nth one on my list actually has an n minus 1 up in the exponent. So this is the sum of the first n values, but it doesn't end at n. It ends at n minus 1, right? Because we started counting at 0. Good, 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 good. Okay, so we're trying to find a formula for this. What does this all add up to? And the trick here is going to be to take the original s sub n. Okay, here it is. We have a, and then we have plus ar to the first power, plus ar to the second power, plus dot 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 dot, plus ar to the n minus 1. And what we're going to do, the trick, is to say, you know what? I'm going to multiply the left-hand side by r, and I'm going to multiply the right-hand side by r, right? As long as we're multiplying both sides of the equal sign by the same quantity, we maintain that equality, right? And then we're going to distribute. So that means that on the right-hand side, each one of these terms is going to get an extra term of r. So I'll end up with r times s of n equals to ar plus ar squared plus ar cubed plus dot 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 dot, right? So I just added one extra term of r to the first power where there was no r, then r squared where there used to be 1, then r cubed, so on and so forth. And then the very last one, it used to be r to the power of n minus 1, but if we add one more r, we add the exponents and we end up with a to the r to the power of n. You know, my r's and my n's look very similar. My apologies. That's an n. This one's an n. Okay, so they all get one extra power of r. Okay, so now what we do is we focus on the following two equations. We have this statement that r times s sub n equals this, and then we have the original s sub n, which was originally equal to this. And what we want to do is subtract them. So we want to do, maybe copy it again. We have s sub n, and we want to subtract from it s sub n times r times s sub n. Okay, so the s sub n was this guy. That's going to be a plus ar to the first power plus ar squared plus dot 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 dot, and ar to the n minus 1 power. Right? This is s sub n minus, and now r sub n, which turned out to be this, right? We're really just adding an extra power of r to each of these terms. So I'm going to zoom out a little bit more. Go over here, go over here. Okay, so then that'll be minus ar plus ar squared plus ar cubed plus dot 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 dot, and then the last one is ar to the power of n. Okay, so then this equals these two. Now I'm going to distribute this subtraction. I'll have a plus ar squared plus, let me throw in one more, ar cubed plus dot 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 plus, and this is ar to the n minus 1 power minus, and then now I'll have ar minus ar squared minus ar cubed minus dot 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 dot, and then I'm gonna go to the one that came right before it, right? So see that these are powers of 1, 2, 3, 4 dot 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 all the way out to power of n. So the one that comes right before it is going to be ar to the n minus 1 power minus ar to the nth power. Okay, and now a bunch of cancellation happens. Ar cancels with this one, plus ar minus ar, plus ar squared cancels with this one, plus ar cubed cancels with this one, dot 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 dot, and then this one cancels with this one. So there's just a massive cancellations, and the only things that survive are the first term, nothing canceled with the constant a, and the very last term, nothing cancels with that last term over there. So what we have, bringing this down, is s sub n minus r s sub n is equal to a minus ar to the nth power. Good. And remember, we're trying to figure out a formula for s sub n, right? So we're going to factor that out. We're going to get that s sub n times 1 minus r is equal to this guy, and again I'm going to factor the a out and say that this is a times 1 minus r to the nth power. And now if we divide both sides by 1 minus r, remembering that this was the case where r, right, so note this was the case where r is not equal to 1. Right? And that's important because if r is equal to 1, then I end up with a 0 and I'm not allowed to divide. But this is the case we're considering where r does not equal to 1. So we get that s sub n equals to a 1 minus r to the nth power divided by 1 minus r. Okay, so we have a formula for s sub n. Now we want to figure out, well, what happens as we let n go out to infinity? And we remember that from before, we know that the limit as n goes to infinity of r to the nth power is going to be equal to 0 for absolute value of r being less than 1. So then the limit as n goes to infinity of s sub n is equal to the limit as n goes to infinity of a 1 minus r to the nth power all over 1 minus r. And we can separate this into two fractions. This is the limit as n goes to infinity of a over 1 minus r minus the limit as n goes to infinity of r to the nth power over 1 minus r. Right, just separating this, a minus ar. Oh, there's an extra a there, sorry. A. Right, so distributing this and separating it as two separate fractions. And then, well, there is no n here, right? The limit as n goes to infinity of something that doesn't have an n. This is a constant as far as this term is concerned. So this part is just going to be equal to a over 1 minus r minus. And then over here, well, again, this is just a constant we can pull out. This would just be a times the limit as n goes to infinity of r to the n over 1 minus r equals that. And again, this is just, there's no n's there, right? So it doesn't get affected. So this is just going to be equal to a over 1 minus r minus a over 1 minus r times the limit as n goes to infinity of r to the nth power. So as we noted above, if r happens to be a value between -1 and 1, then we know that this is going to go to 0. If r is between 1 and -1, some value there, we know this goes to 0, which means that the entire thing goes to 0, which means that this is the only thing that survives. So we get a over 1 minus r. Zoom out and bring it all together. So this is the limit as n goes to infinity of s sub n, right? This is the same. Okay, so we have another case here. The case where r equals to 1, we covered that up here. If r equals to 1, right, all of these r values become 1, then that's easy. We end up with a summation of a plus a plus a plus a plus a plus a going on forever. It's going to add up to either positive or negative infinity depending on whether the a is positive or negative. Now we're considering a separate case. What if we have r not equal to 1? We already covered 1. What if it's not equal to 1? Well, okay, so we tried this little thing. We tried this little idea of distributing an r and doing all of this. We got a little formula for s sub n. And if r doesn't equal to 1, we get this little formula. And now we see that as n goes to infinity, that this is going to converge to this, right? When r is between -1 and 1, this part goes to 0, therefore the limit exists and it equals to this. So let's look at the summary your author did. A little neater than mine. Right? So if r equals to -1, we have that s sub n equals to this. And then if we distribute an r going across here, we have an extra power of r. So we have ar, that's going to become this term. Ar squared, that becomes this term. And so on and so forth. So each one of these terms has an extra power of r. If we multiply both sides by r, that's where this guy comes in. And then we subtract them, this one minus this one. That's how we get this. And then this one minus this one, a bunch of stuff will cancel. And so it's just this term minus that term. Good. Factor out. Divide both sides by 1 minus r. And that's how we get to this. Right? This is the same formula that I got over here. This formula. Okay. And now we know that if r is between -1 and 1, we know that r to the nth power goes to 0 as n goes to infinity. And so the limit as n goes to infinity of s sub n is equal to the limit as n goes to infinity of this guy, right? This was our formula for s sub n. We can separate that into two separate fractions. The first fraction, well, the limit doesn't apply to it. There is no n's in there. For the second fraction, right? For the second fraction, again, we can separate the constants of 1 over 1 minus r because there's no n there, right? This limit only affects the n, the terms that have an n in them. And now we know that this will go to 0 whenever this is true. So if r is between -1 and 1, then the limit exists and it's equal to this formula. Good, good, good. Now, if r is less than or equal to -1 or r is greater than 1, then we know that the sequence r to the nth power is divergent, right? It keeps growing out of control. So, think of, for example, if r equals to 2, 2 to the nth power is going to grow out of control. So it diverges. Okay, and so we can bring these things together, all these cases together, into the following little summary for geometric series. So if we have a sum from 1 to infinity of ar to the n minus 1 power, it looks like this, right? Dot, 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 ar to the third, ar to the fourth, ar to the fifth, dot, 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 forever. Well, we can conclude that that summation forever, that the sum of the series, that it converges if the absolute value of r is less than 1. That means that r is a value between -1 and 1. And that sum, that series, will be equal to a over 1 minus r. On the other hand, if r is anything other, less than or equal to -1, or greater than or equal to 1, then the series diverges. Good. So it's only convergent for r being, absolute value of r being strictly less than 1. Notice that it's strictly less than. It's not, the formula here doesn't include the 1. Does not include being equal to 1. Okay, let's look at another series. And we'll look at some examples with your homework soon so that we can apply some of these things. Show that the harmonic series is divergent. Okay, so this is a classic example because of the following thing. We said that if we start adding a bunch of numbers that go on to infinity, so we looked at early on an example, something simple like 1 plus 2 plus 3 plus 4 plus 5, dot, 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 dot. Say we look at something like this. If I wanted to add all these numbers out forever, obviously they're not going to add up to any constant because they just keep getting bigger and bigger and bigger and bigger, right? So one of the important things for something to even have a chance to add up is that that the individual terms can't be getting bigger. Okay, what if they don't get bigger? They just stay the same. Well, what if we just had 2 plus 2 plus 2 plus 2 plus 2? Okay, well, in this case, the individual terms are staying the same, but still, obviously, these aren't going to add up to anything. They're going to grow up to infinity, right? This is going to head toward infinity if we add the whole thing up, and this is going to head toward infinity as well. So it's important for the individual terms to get smaller. If you have any chance that the entire sum is going to add up to some constant value, then it must be true that that the individual terms are getting smaller. Okay, then we consider this series: 1/2, then 1/4, then 1/8, then 1/16, dot 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 dot, and we saw that this whole thing just adds up to 1. Right? This is that classic pi situation. You eat half the first day, a fourth the second day, an eighth the next day, and so on and so forth forever, and they just add up to 1. Right? A little counterintuitive that this infinite list of fractions, all of them added up together, just add up to 1. Right? But we can see that visually with that classic pi slicing situation. So we can see that one of the criteria in order for the series to converge to anything is that the terms must be getting smaller. Okay? But just because they're getting smaller, it's not good enough, as this series shows us. Because here the terms really are getting smaller: 1, 1/2, 1/3, 1/4, dot 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 dot. But they actually diverge. They don't converge. Right? They just getting bigger and bigger and bigger. So let's explore why that is. Okay, so we want to show that 1 plus 1/2 plus 1/3 plus 1/4 plus dot 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 dot, that is still going to infinity, even though the individual terms are getting smaller. Right? Getting smaller is not good enough. We have to be getting smaller at a fast enough rate. Right? It's getting smaller. The individual terms are growing towards 0, but they're not growing fast enough. And so the sum is still going out of control, and the whole thing is still adding up to infinity. Okay, how to show this? Let's look at the partial sums. Okay, so let's create the list of partial sums. Well, S sub 1 is going to be the sum of the first one. That's just 1. S sub 2, that's going to be 1 plus 1/2. That's 2 over 2 plus 1 over 2, which is equal to 3/4. Oops, sorry, 3 over 2. 1/2. Okay, then S sub 3 is going to be 1 plus 1/2 plus 1/3. Okay, so, and then S sub 4, let me leave that alone for a second. Then S sub 4 is going to be 1 plus 1/2 plus 1/3 plus 1/4. Okay, and then S sub 5, that's going to be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. And S sub 6 is going to be equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6. 1, 2, 3, 4, 5, 6. Okay, so one of the common tricks in this, well, I don't know if it's common, but one trick is to group these up in a way that makes it clear that it's either larger or smaller than something that's easier to deal with. So instead of having all these fractions with different denominators, let's group them up. Okay, so someone way smarter than me came up with this. So don't assume that you're expected to do this on your own. But it's nice to at least recognize, what somebody else has done. And so what we're going to do is focus on the partial sums that are indexed by powers of 2 here. So for example, we're going to focus on this one and this one, and then the next power of 2 is going to be 8. So I'm going to kind of skip on down. We have S sub 7, and then I'm just going to write down S sub 8. That's 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1 over 7 plus 1 over 8. Okay, and so we're looking for patterns. So notice the first pattern is that as I'm adding fractions, this one is 2, and it ends in a 2 over here, right? This one was just going to be 1/2. You know what? Actually, I don't really want this here. Let's just leave it alone like that. Okay, so this one's 1 plus 1/2, so notice that this matches that. And then with this 4, that this matches this guy over here. And with the 8, of course, that it ends in 1 over 8. Okay, so now what I want to do is, with this guy, notice that if I kind of think about these last two there, 1/3 is about 0.333333. It's bigger than 1/4, which is 0.25, right? This one is 0.3 bar, 33333, and this one is 0.25. So this one is definitely a little bit bigger. So what I could do is I could rewrite it or think about it as, or think about this, 1 plus 1/2 plus, and then insert a 1/4 instead of the 1/3, plus a 1/4 there. So, you know, I'm not doing anything to this one. I'm not manipulating it in any way. I'm just saying, consider this one. Is it clear then that this one must be a little smaller than this one, right? Smaller. That's all I'm saying. Look, this one's smaller. Good. And the reason why that's useful is because now this is easy to add. It's just 1/4 plus 1/4, that's a half, isn't it? So this is equal to 1 plus 1/2 plus 1/2. And that's easy to add up. That's just 1 plus 1. 1 plus 1. Or 2. Okay? All right, now we're going to skip on down and come down here to powers of 8 and do the same thing. So we have a 1, except over here, I'm going to group them up a little bit different. I already had these from before. And then I'm going to group up these. And I'm going to say that, let's compare it to this one and the 1/2. So this is just the first two. And then these two, just like before, I'm going to compare it to having a 1/4 plus another 1/4, right? And clearly I've kind of exchanged this 1/3 for a 1/4, which is a little bit smaller. That's why there's less than. I'm saying this new sum is definitely smaller than this one, right? So this, whatever this adds up to, is going to be bigger than this one. Good. And now I'm going to do the same thing with these, except I'm going to note that each one of these, the 1/5, the 1/6, the 1/7, they're all decimals that are a little bit bigger than 1/8. 1/8 is the smallest of them all. So if I replace this one with a 1/8 and I replace this one with a 1/8, or not replace it, maybe compare it to is the better term. Compare it to this. Okay, I'm going to put them over here. This is going to be plus 1/8 plus 1/8 plus 1/8. And then there was the actual 1/8 plus 1/8, right? So these red 1/8s come from me considering these and not algebraically, right? People get stuck with this because you're thinking, oh, did you add both sides? Did you multiply both sides? This isn't about both sides. I'm just saying here, consider this new number, this new list of numbers here. Because I made a very careful replacement of each one of these fractions with a different fraction that's definitely a little bit smaller, I can definitely say this new sequence of fractions is going to be smaller, right? These ones are smaller than that one. And the reason why it's useful to do this is because now we get to group them up in a nice, pretty way. These guys group up to just be 1/2, and these guys group up to just be 1/2. So I end up saying that this list here is definitely bigger than 1 plus a half plus another half plus another half. 1, 2, 3 halves. Good, 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 good. Okay, so this ends up being 1 plus 3 over 2. So we have that s over 8, s over 8, which was equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/16 plus 1/7 plus 1/8 is equal to this. Okay, one more thing. Instead of calling it an 8, though, I'm going to refer to it in powers of 8. I'm sorry, powers of 2. So I'm going to rewrite this guy as 2 to the power of 3. And then I'm going to note that this guy is a 3. Okay, I'm going to do one last one. It's going to be crazy ugly, and then we'll be ready to establish our pattern, I think. We're going to look at ... We're going to jump all the way down to s sub 16, right? I'm looking at powers of 2, which is the same thing as s sub 2 to the 4th power. Okay, and we know that that's going to be this very long list. 1 plus 1/2 plus 1/3, plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9 plus 1/10 plus 1 over 11 plus 1 over 12 plus 1 over 13 plus 1 over 14 plus 1 over 15 plus 1 over 16. Ugly. Okay, and then we're going to group them up just like before. I already know I want to group up these two. Oops. I want to group up these two, right? And then I want to group up these guys. And now I want to group up these guys. Good. And I want to think about this brand new sequence, right? So I'm not manipulating both sides. I'm not getting a common denominator. I'm not doing any of that. I'm just saying, hey, consider this new list of numbers that's very similar, just a little different. The first two are the same. And then I exchange this one, 1/3. I exchange it, or I think about a new fraction that's a little smaller. Oops, 1/4. A little smaller, 1/4, right? That one turned into 1/4 plus 1/4. So automatically this new list is going to end up being smaller than the previous one, right? So I'm saying that s sub 2 to the 4th power is going to end up being a little bit bigger than this new one when I finish with it. I'm not done with it yet. So now these, we're going to replace each one of those with an eighth, 1/8, plus 1/8, plus 1/8, plus 1/8, plus, and now I'm going to replace each one of these with a 1/16. 1 over 16, plus 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 1 over 16. Okay, let's see where they all matched up. So hopefully this one went to there, right? This one was matched up with this one. This one was matched up with that one. This one was matched up with that one. So on a case-by-case basis, this bottom one is either equal to or smaller than the top one, right? 1/3 is bigger than 1/4. 1/5 is bigger than 1/8. 1/6 is bigger than 1/8. 1/7 is bigger than 1/8. 1/8 is equal to 1/8. 1/9 is bigger than 1/16. 1/10 is bigger than 1/16. 1/11 is bigger than 1/16. 1/12 is bigger than 1/16. 1/13 is bigger than 1/16. 1/14 is bigger. That one's bigger, and then that one's equal. Okay, so we've established that, hopefully, that this is definitely bigger. This original list that we're interested in is definitely bigger than this new list. And again, the advantage is that now they group up nicely, right? This is easy to tell that this is just going to be 1/2, and this is just going to be 1/2. And this is just going to be 1/2, right? Coupled with the original 1 plus 1/2, I get this ugly mess, right? And all of that is bigger than my original value, like that. And so s to the 2/4 is greater than 1 plus, and then I have 1, 2, 3, 4 over 2, right? And again, notice the pattern. Right? 2 to the 4th is greater than 1 plus 4 over 2. Good. Okay, so now we're ready to see the pattern. So let's see how your author organized all this. Okay, so s sub 2 is equal to 1 plus 1 over 2. Okay, notice that this is the same thing as 2 to the power of 1, this little subscript here, and that matches this one. Then for s sub 4, which is the same thing as 2s to the power, this is the same thing as s to the power of 2, 2 to the power of 2, right? That's s sub 4. And then that matches with this little guy right there. Okay, then we did it for 8, s sub 8, right? Which, again, this is the same thing as s sub 2 to the power of 3. Good. And so we get the original list, and then we compare it with a new list that's definitely a little bit smaller, and then that new list allows us to simplify it down to this, and again, it matches this. Good. And then we did it for 16, right? And so this is the same thing as saying s sub 2 to the power of 4 is equal to s sub 16, and then we have the original list, right? And then we group them up. We find a new list that's definitely a little bit smaller, and they group up in a really nice way, so we end up with this, and we end up with this power. Okay, so let's it's really big, a lot of stuff's going on, so let me just summarize it for us. We have s sub 1, and then we have s sub 2, and s sub 2 is equal to 1 plus over 2, s to the power 2 to the power 1 is equal to that. Okay, and then there's an s sub 3, we didn't touch that. S sub 4, however, s sub 4, well, that's actually equal to s sub 2 to the power of 2. That's what s sub 4 is. And after a bunch of work, we saw that that equals to 1 plus 2 over 2. Okay, and then, then there's an s sub 5, we didn't touch that, an s sub 6, we didn't touch that, s sub 7, we didn't touch that, s sub 8, okay, and an 8, again, can be written as 2 to the power of 7. S sub 8 can be written as 2 to the power of 3. And we saw that that was equal to 1 plus 3 over 2. Okay, so we start to see a pattern, right? And then the last one we actually did, was 16. So this is s sub 8, then this s sub 9, s sub 10, right? A bunch of ones that we didn't touch. But then we focused on s sub 16, which is equal to 2 to the power of 4. And that one is equal to 1 plus 4 over 2. And now we start to see the pattern, right? So so there's a bunch of s's. The next one is s sub 17, and then s sub 18, Okay, but amongst those is going to be the ones that happen to be powers of 2. So if we land on, or the next time we land on another one, s sub 2 to the power of some value n, then we know that the formula for this one, oh, you know what? I messed up this entire time. It's not that it equals that. Sorry. We've established inequalities, right? We're saying that it is bigger than that. Bigger than that. It is bigger than that. It's bigger than that. And so this is bigger than 1 plus n over 2. Good. Okay, so that's the little formula we have. So now, when we want to think about the limit as n goes to infinity, as n goes to infinity, this is just going to diverge, right? As n gets bigger and bigger and bigger and bigger, this whole thing is going to get bigger and bigger and bigger. So we want to put it together this way. The limit as n goes to infinity of s sub 2 to the nth power is equal to the limit as n goes to infinity of 1 plus n over 2. And this diverges, this heads off to infinity. So we can conclude then that the limit as n goes to infinity of s sub n is also going to go off to infinity. Good. In other words, we had s1, s2, s3, s4, ... We've shown that if we just focus on the powers of the ones that end up with powers of 2, like this one, this one, this one, if we just focus on those, we've shown that those go off to infinity, right? And so we didn't actually show that each individual one, we never really touched the 1, the 3, the 5, for instance. But clearly, if every as we go through this and we land on all the powers of 2, those guys go to infinity, then the entire sequence must go off to infinity, right? If we can show that this one goes to infinity, and then if we look at s sub 8, and then we look at s sub 16, and then s sub 32, and then s sub 64, right? If we just focus on all the ones that have a subpower of 2, and those guys are going off to infinity, it'll just drag the whole thing along with it, right? There's no way that the rest of the sequence, the ones we didn't really look at, there's no way that those guys do anything different. Right? Remember, we're adding a bunch of positive fractions anyway. Okay, so then the whole thing must head off to infinity. All right, so let's see. So over here. Okay, so the author pointed out a couple more examples of powers of 2. Note that 32, that's 2 to the power of 5. That's why we get 1 plus 5 over 2. And 64 is 2 to the power of 6. That's why we get 1 plus 6 over 2. And so we end up with this as our general statement for powers of 2. And the limit as n goes to infinity goes off to infinity, right? It diverges. And so the harmonic sequence diverges. Okay, so that leads to the following theorem. If the series a sub n, as n goes from 1 to infinity, is convergent, then it must be true. Then you can conclude that the individual terms converge to 0, right? However, the reverse is not true. Just because the individual terms are going to 0, we cannot conclude that the sequence is convergent. Okay, so one directional. A series is convergent. We know that it must be true that the individual values of the sequence must converge to 0. The limit as n goes to infinity of a sub n must be equal to 0. But just simply knowing that the individual terms are going to 0 is not good enough to conclude that the series is going to converge. All right, the test for divergence. If the limit as n goes to infinity of a sub n does not exist, or if the limit does not equal to 0, then the series is divergent, right? So that we can conclude. If we look at the individual sequence values and we see that either the limit does not exist or it does not equal to 0, right? Then the series diverges. The test for the divergence follows from Theorem 6, because if the series is not divergent, then it is convergent, and so the limit as n goes to infinity at a sub n equals to 0. Okay. All right. Final thoughts here for this section, and then we'll look at some homework problems. Theorem: if the series a sub n and the series b sub n are convergent series, then so are the series c times a sub n, where c is some constant, and a sub n plus b sub n, the series a sub n plus b sub n, and the series a sub n minus b sub n, and the following are true. Okay, so this first one is saying that if we have this series with a constant, we can factor it out. Right, this c represents some constant that is not affected by the index of the Riemann sum here, n. So we can pull it out. This one is saying that if we have a summation in parentheses of the Riemann sum, so a Riemann sum of a sum is equal to the sum of two Riemann sums. Good. And then the same thing with the difference. So we can separate it into the Riemann sum of a difference is equal to the difference of two Riemann sums. Good. So some properties that we get to use as we work through some of these. Okay, I know that was a lot, so let's dive into some homework problems and see how we use some of this stuff. Okay, so here are your homework exercises from Chapter 11, Section 2. You were assigned, starting with number 11. Let's see here. Calculate the first 8 terms of the sequence of partial... So from 5 to 8, calculate the first 8 terms of the sequence of partial sums, correct to 4 decimal places. Okay, so those just seem like a little bit of busy work to figure out how to find these, but I think they're pretty straightforward, right? Let's just do like number 5 real quick, or at least just get it started. So what number 5 is saying, let's do that one. This is Chapter 11, Section 2, number 5, and we have this sum of n to the 4th power plus n squared 1, n goes from 1 to infinity, and it just says calculate the first 8 terms of the sequence of the partial sums. The sequence of partial sums, correct to wait for 4 decimal places. Does it appear that the series is divergent? Okay, so this series is describing the following. Okay, so when n equals to 1, we get 1 to the 4th, 1 to the 2nd. That's just going to be equal to 1 over 1 plus 1. Plus, okay, when n equals to 2, ooh, that's just going to get really ugly real quick. 2 to the 4th power, that's equal to 16, plus 2 to the 2nd power, which is equal to 4, all over 1. That's already pretty ugly. 1 over 3. 3 to the 4th power is 81. And then 3 squared is, 3 squared is 9. So we end up with that. Plus dot, 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 dot. Okay, so this is the values of the series. That's going to be 1/2 plus 1/20th plus 1/90th. Plus dot, 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 dot. Okay, so you keep going that way. And now the partial sums, right? S sub 1 is just going to be equal to 1/2. S sub 2 is going to be equal to 1/2 plus 1 over 20. Common denominator, figure out what that is. S sub 3, that's going to be 1/2 plus 1/20th plus 1/90th. Good. S sub 4, okay, well you have to figure out what the 4th one is by putting a 4 there. 4 to the 4th plus 4 to the 2nd. That'll be the next term in the series, and then we need that one to figure out the 4th partial sum. And so this hopefully will get you going, figure out where you need to go. I think feel free to use technology in this, for these questions. I don't think they really intend for you to go into the big numbers by hand, but the idea is fairly simple, right? And it says to do what? The first, calculate, do 4 decimal places, the first 8 terms. Okay, well, we did the first 3, 5 more to go. Okay, but I think those are fairly easy to do. They're just long and tedious. 9 through 14, find at least 10 partial sums of the series. Graph both the sequence of terms of the sequence of partial sums on the same screen. Does it appear that the series is convergent or divergent? If convergent, find the sum. If divergent, explain why. Okay, so let's look at number 12. Okay, the series is 7 to the power of n plus 1 all over 10 to the nth power. And it does have this little symbol up here, which means that we're allowed to use technology. Our graphing calculators or Desmos will do just fine. So let's first of all play around with that and get the graphs and see if we can see some pattern out of this. Okay, so first of all, let me go over to Desmos, and let's get rid of that, and let's get rid of that, and we're going to add a new table, and let's make this n, and this guy is going to be equal to 7 to the power of, in parentheses, there's an n plus 1, close parentheses, and then the whole thing gets divided by, it was 10 to the power of n. So there's my formula. So when it equals to 1, when n equals to 1, we get 7 to the second power, that's 49, divided by 10 to the second power, that's 100. 49 divided by 100 is 4.9. Okay, that looks good. And then 2, and then 3, and then 4, and then 5, and then 6, and then 7. Okay, so the individual terms of my series, that's these guys, they seem to be heading towards 0, right? So that's the first important criteria. If the individual terms were not heading towards 0, right away we know that the series diverges, right? So it's important and required for the individual terms to be heading to 0, but that's not good enough. Just because they're heading to 0, I can't throw my arms up and go, okay, well, that means that the series converges. No, we don't know that. Not only do they have to converge to 0, but they have to go towards 0 fast enough, right? So does this go to 0 fast enough? Okay, so now we need a way to add these up. Okay, so we need a way to add up the partial sums. And for that, I'm going to go back to this style over here, or this file over here, and realize that this looks an awful lot like a geometric sequence, right? So I'm going to say that this is the same thing as this, n equals to 1 to infinity of 7 times 7 to the nth power divided by 10 to the nth power, right? Because, right, I can put a little 1 there. These two combine to give me this one. And now these two can combine to say that that's the same thing as this. To the nth power. And now I'm almost there. If I just take one of these out of here, I end up with the sum, as then goes from 1 to infinity, of 7 times 7 tenths times 7 tenths to the power of n minus 1, right? Because this is 1. So if I add these two together, I get that one. And now I'm done. This whole thing here becomes 49 over 10. This becomes sum, as n goes from 1 to infinity of 49 tenths times 7 tenths to the power of n minus 1. This is a geometric sequence. Remember geo? Remember a geometric looks like this. Riemann sum as n goes from 1 to infinity of some constant r to the power of n minus 1, like this. And we know it converges to a over 1 minus r if the absolute value of r is less than 1. And that's what this is, where r, so for us, this is the part that is the a, some constant out in front, 49/10. And then this guy here, 7/10, that's the r. And 7/10 is less than 1, so we're good. It's going to converge. Now it's going to converge to this at infinity, but also we saw from our formula, from our work before, that in a geometric sequence, so for a geometric series, we found the value of s sub n. The value of s sub n was equal to a 1 minus r to the nth power all over 1 minus r. So if we stop at any value of n and we just wanted to find the sum of the first n numbers, right? This is a formula, a closed formula for a partial sum. Okay, so the only reason I bring this up is because this will be useful for Desmos. When I want to figure out the sum of the first one, or the first two, or the first three. That's the formula I'm going to use. So s sub 1 is going to be this formula where we put a little 1 there. So it'll be equal to 49 over 10. That's just going to be equal to 4.9. So it'll be 4.9. 1 minus, and then r, well, that's just 0.7. 0.7 to the power of 1 divided by 1 minus 0.7. Okay, that's kind of ugly. And that's just replacing this 1 here with this 1 right there. Okay. Now, to find the next one, s sub 2, well, that's going to be equal to 4.9, 1 minus 0.7 to the power of 2. Let's put it in color. S sub 2, power of 2. And then the whole thing gets divided by 1 minus 0.7. Okay, so dot, and that's how I find the first partial sums. If I wanted to find, let's just kind of randomly jump to, say, s sub 7. The sum of the first 7 numbers in this series, well, that's going to be 4.9, 1 minus 0.7 to the power of 7. Okay, so let's now use our calculator to figure out what this is. This is 7 there, right? Just matching the pattern. I just arbitrarily pick 7 just so that we can confirm once we do it on Desmos that we get the same answer. So let's go to our calculator. It's clear. All right, so it's going to be 4. Let's start with the decimal. I'm going to start with 0.7 to the power of 7. I get that. And then it's 1 minus that answer, 1 minus the previous answer. Gives me that. So that should be this part in parentheses. And then we multiply that times 4.9. And we get the numerator. And then that whole thing gets divided by 1 minus 0.7, which is just going to be 0.3. That gives me 14.9882. 14. 14.9882. 9882. Okay, so that's just the sum of the first 7 terms of our series. Let's confirm it with Desmos and see how that goes. And this is the formula I'm going to use for Desmos, right? It tells me the sum of the first n values, partial sums. So it is equal to this guy. So it is 4.9. So in parentheses, it's 4.9 times, parentheses again, 1 minus, parentheses again, 0.7 to the power of n, close parentheses again, divided by, parentheses, 1 minus 0.7, close parentheses. Okay, well that's an ugly formula, but hopefully we typed it all in right. It's just repeating this formula right in here. This one right in here, except we replaced it with an n instead of this number. Right, so it's 4.9 times 1 minus 0.7 to the nth power, all over 1 minus 0.7. We could have simplified it, obviously. We could have had this number divided by this number times 1 minus 0.7 to the power of n. Let's simplify that a little bit. We could have, we have this one, 4.9 times 1 minus 0.7 to the power of n, all over 1 minus 0.7. So this whole thing is really just 0.3, 0.3. And so we can divide 4.9 divided by 0.3. 4.9 divided by 0.3. S sub n equals to 16.33333, right? It goes on forever. Times 1 minus 0.7 to the nth power. So I could simplify it and type this into the formula instead of this one. Let's type it over here. 16 point bunch of 3's times 1 minus 0.7 to the power of n, close parentheses. See, you get the exact same thing. Good. Okay, either way, let's confirm that it makes sense. So the first one, yeah, this is the terms, the individual terms of my series, and these are the partial sums. So S sub 1 equals this. S sub 2, which is the sum of these two, equals this one, right? If we add these two, they give you that one. S sub 3, which is the sum of the first 3, adds up to this one. S sub 4 equals this one. S sub 5, S sub 6, S sub 7. So this is the one we found by typing it into our formula. Good. Okay, it makes sense. These are the partial sums. And now we can graph them. Let's get rid of that. We can graph them, and we can see them over here. Here are the partial sums. These are the individual terms. The individual terms seem to be going to 0, and the partial sums seem to be heading somewhere as well, right? There seems to be a max, like a roof somewhere. You can keep going. You can see that there seems to be a plateauing, right? And we can see from our sums here, they seem to be heading towards 16.333333 maybe. So let's graph that. Y equals to 16.33 like that. Or you can type in 1/3. And let's make that in red. Red. So visually we could see that the individual partial sums, right, the sum of the first 2, the first 3, the first 4, the partial sums seem to be heading somewhere, right? And we've already established there was a geometric sequence, so we can figure out what that is, but we've shown it graphically. Okay, let's go back and figure out what that is. Okay, so it is a geometric series, And we know that a geometric series converges as long as r is, absolute value of r is less than 1, which it is in this case. So it'll converge to this. So for us, we had this goes from 1 to infinity, and we had 4.9. So this is a geometric series. With a equal to 4.9 and r equal to 7/10, which is 0.7, which is less than 1. So it converges to a over 1 minus r which is equal to 4.9 divided by 0.3, which is equal to 16.33333, right? Which is exactly what we saw over here. They are converging toward that number indeed. Okay, make sure you use technology for these questions. You don't want to do all of these calculations by hand. They can get a little heavy, especially since they asked for 16 terms, I think they asked. Find at least 10, right, to do the first 10, so that could get a little tedious if you're doing it by hand. All right, let's try another one. Moving on, and that's for those. Okay, 16, 17, okay, starting with 17 to 26, determine whether the geometric series is convergent or divergent. If it is convergent, find the sum. Okay, big hint, these are geometric, right? It says determine whether this geometric series is convergent. So all we have to do is establish if the r in a geometric series is if its absolute value is less than 1 or if its absolute value is greater than 1. Okay, so why don't we start with, say, something like number 18. Chapter 11, section 2, number 18. And so this one just gives us the numbers 4 plus 3 plus 9 over 4 plus 27 over 16 plus, and then they feel like the pattern has been established at that point. Okay, so it's going to be a little bit of work to figure out how to get these. Okay, remember that a geometric has the following pattern. For this to be a geometric series, as we were told, is this one, and goes from 1 to infinity of ar to the n minus 1, right? And so if we let n equal to 1, then we end up with just a plus ar plus ar squared plus ar cubed plus dot 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 dot. Okay, so each individual term is going to have a constant times a value of r, and this is r to the first power, and so we just keep, to get from one term to the next, we always multiply by r. Right? To go from here to there, multiply by r. That's what geometric series are. They're a case where to get from one term to the next, we always multiply by the same constant. So we can figure out what that r is. Okay, well, we have a bunch of values in order here, so all we have to do is find the r. So this times blank equals that one. That's what we want to say. Notice that if I took this one and divided by that one, ar squared divided by ar to the first, the a's cancel, one of the r's cancels and we just get r. If I take this one and divide it by that one, ar to the third divided by ar to the second, a's cancel, two of the r's cancel, and we're left with just r. Okay, so all along the way, if I take one of the terms and divide it by the one that came right before it, I'm going to get the value of r. So that's exactly what I'm going to do here. Now you can do it with any one of these, so why not choose the easiest two to get, right? Why not just use these two? So I'm going to do 3 divided by 4, that equals to r, right? Or I could have also done r equals to 9/4 divided by 3, right? Which then simplifies to 9/4 times 1/3, and then this cancels with that, giving me 3/4. Okay, I also get r that way. I could have also gotten it through this one. Or r equals to 27/16, the whole thing divided by 9/4, which then equals to 27/16 times 4/9, and then 4 cancels with that, giving you a 4th, 9 cancels with that, giving you a 3, and so you still end up with 3/4. Okay, so we've definitely established that r equals to 3/4. Okay, and then, well, a equals to that first term. So a equals to 4. So let's put it into our series and just kind of guess and check and see if any tweaks need to be made, right? So we kind of are establishing, we're hoping that it's true that the sum, as n goes from 1 to infinity, of 4 times 3/4 to the power of n minus 1, that equals to this thing. It equals to the list that they gave us. 4 plus 3 plus 9/4 plus 27/16. Okay, so do a little bit of work, get some values, check them, and make sure. Okay, if n equals to 1, this becomes 0, so we just get 3/4 to the power of 0 is 1. That's just going to be 4. Okay, yeah, we get that first term. If n equals to 2, we end up with 2 minus 1 is going to be 1. So we just get 4 times 3/4. The 4's cancel, we just get a 3. Yep, that one works. If n equals to 3, we get a squared up here. So we get 9/16. 4 is reduced, so we get 9/4. Yeah, so this seems to be working. Right, so we have a geometric, right? So this is a geometric with a equal to 4 and r equal to 3/4, and that is less than 1, so it is convergent. So convergent. Right? And furthermore, what does it converge to? The whole thing will converge to a over 1 minus r. So it'll be 4 over 1 minus 3/4, which is equal to 4 over 1 minus 3/4 is equal to 1/4. So the whole thing equals to 4 times 4, which equals to 16. Okay, so that infinite sum, 4 plus 3 plus 9/4 plus 27/16 plus dot, 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 forever, that infinite sum will add up to 16. Good. If you know someone that's turning 16, you could put this on their cake, right? Here's their birthday cake. Happy 4 plus 3 plus 9/4 plus 27/16 plus dot 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 birthday. Right? And as long as this goes on forever, then it's going to be exactly 16. If we ever stop anywhere, then you're not quite at the 16. Right? You don't quite make it. Even if you go out pretty far, let's say you add the first 1 billion fractions here, that's still not quite 16. You got to go on forever, infinity. Okay? These are fun. Hope one of you guys does one of these birthday cakes soon. Okay, let's go back to the work. What else we got? Did we answer it? This was number 18. Determine whether the geometric sequence is convergent or divergent. If convergent, find its sum. Okay, so we did number 18. 20 is similar, right? They already told us it's geometric, so it's just up to us to figure out what the A is and what that constant is, right? And it should be pretty easy to go from 2 to half, right? Maybe multiply by a fourth. 1/4, 1/4, 1/4, 1/4. So R is going to be equal to 1/4. A is equal to 2. Plug them into our equations and everything should work out well. Okay, let's keep going. How about something like number 22? That looks interesting. Okay, pi to the nth power. Remember, pi is just a number. We can think about it as 3.14, although we know it's not quite that. It keeps going. It's an infinite number, never a repeating pattern. So let's play with that one and see if it fits a neat form for our geometric series. So this is chapter 11, section 2, number 22. So we get n equals to 1 and then some infinity and 5 over pi to the nth power. Okay, so in order for it to be a geometric, it must be that I can manipulate this, rearrange it so it fits the form of some constant times some other value r to the power of n minus 1, as n goes from 1 to infinity, right? This is a geometric. Okay, so I'm just going to manipulate this a little bit, do a little bit of algebra. This is the same thing as 5 times 1 over pi to the nth power, okay, which is equal to this guy, n equals to 1, and then I'm going to rewrite it as 5 times 1 over pi times 1 over pi to the power of n, right, because this is to the power of 1. So these, n minus 1. So these two combine to give me this one. Good. And so now these two would combine to give me my constant A. This is just going to be equal to 5 over pi. That's my A. And then 1 over pi, that's my R to the n minus 1. Good. This is a geometric. Geometric with A equal to 5 over pi and R equal to 1 over pi. Since 1 over pi is definitely less than 1, right, and you get some decimal that's smaller than 1, then we know it converges. Converges. And what does it converge to? That whole sum, that infinite sum, is going to converge to A, which is 5 over pi, divided by 1 minus R, which is equal to 1 over pi. Okay, well that gets ugly. It's not a pretty way to simplify this, I don't think. Pi over pi, that's just going to be equal to 5 over pi divided by, if I put a pi over pi, that I end up with pi minus 1 over pi, like this, which is equal to 5 over pi times, and now multiply the numerator times the reciprocal of the denominator, we end up with this, pi minus 1, and now the pi's cancel, and so we end up with 5 divided by pi minus 1, right? Good enough. Or you can just approximate that with your calculator. How about something like number 28? Determine whether the series is convergent or divergent. If it is convergent, find its sum. Okay, so that's an interesting one. Chapter 11, Section 2, number 28. And we're given 1/3 plus 2/9 plus 1/27 plus 2/81 plus 1/243 plus 2/729 plus dot 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 dot. Okay, so the denominator is clearly powers of 9, but the numerator alternates between 1 and 2, 1 and 2, 1 and 2, 1 and 2. So, okay, we can rewrite this as 1/3 plus 2/3 squared plus 1/3 cubed plus 2/3 to the 4th plus 3 to the 5th plus 2/3 to the 6th plus dot 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 dot. Okay. So what we could do is regroup them. So let's regroup them as 1/3 plus 1/3 to the 3rd power plus 1/3 to the 5th power plus 1/3 to the 7th power plus dot 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 dot, like that. So we took all the ones that have a numerator of 1, and then this thing, right, out to infinity, I'm going to add it to this other one, which is going to be all the ones that have a 2 in the numerator. So 2/3 squared plus 2/3 to the 4th power plus 2/3 to the 6th power plus dot 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 forever. Okay, so let's examine each one of these. So these have powers that are odd, 1, 3, 5, 7. And these are powers that are even, 2, 4, 6, 8. Okay. So this is a geometric sequence where to go from one term to the next, we always multiply by 1/3 squared, starting at 1/3. Right? So 1/3 times 1/3 squared gets you to 1/3 cubed, and then 1/3 cubed times 1/3 squared is going to get you to 1/3 to the 5th, and so on and so forth. So this is a geometric, geo, where n goes from 1 to infinity. The first term is going to be 1/3 times the r is going to be 1/3 squared to the power of n minus 1. Right? Guess and check. So I just kind of guessed it, and then we can check it. Is it true? Does it work out? When n equals to 1, I'll get a power of 0, which means this will be 1. So I just get the 1/3. When n equals to 2, I'll get 2 minus 1 is just 1. And so I'll get 1/3 to the 2nd power times 1/3. That's 1/3 to the 3rd power. That works out there too. Good. Okay, so it works out every time. And then over here, this is also going to be a geo, where to go from one term to the next, we multiply by the same thing, times 1/3 squared. Right? This times 1/3 squared gets you 2/3 to the 4th. And this multiplied by 1/3 squared gets you to 2/3 to the 6th. So this is also going to be a geometric series that goes from 1 to infinity of the first term, which is equal to 2/3 squared times 1/3 squared, and the whole thing raised to the power of n minus 1. Again, if you do a little guess and check, you can see, you can confirm that it all works out. And since they're both geometric series with, here's one where a, here, a equals 1/3, and r equals to 1/3 squared, which is 1/9. And 1/9 is definitely less than 1, it converges. And it converges to 1/3 all over 1 minus r, which is equal to 1/9. Good. So this will be equal to 1/3 divided by 8/9, right? 9 over 9 minus 1 gives you 8/9, which is equal to 1/3 times 9 over 8. This reduces to 3. This equals to 3/8. Good. Okay, same thing for this one. This is a geometric where the a value equals to 2 over 9. It's this thing. And the r equals 1 over 9, which is still less than 1. So it converges as well. And it converges to 2/9 divided by 1 minus 1/9, which is then equal to 2/9 divided by 7. Sorry, this is divided by 8/9. So then equals to 2/9 times 9 over 8. The 9's cancel. The 2 and the 8 reduce. And so the whole thing equals to 1/4. Okay, so going back to the original list, right, here's that original list, and then we just manipulated a little bit to simplify it. Then we separated into two separate ones, and they were both kind of going out to infinity, right? So it's this one of all the odd ones going out to infinity, plus this one of all the even ones going out to infinity. And we just figured out that this thing over here, this whole thing is geometric and it converges to 1/4. And this thing is also geometric and the whole thing out to infinity of these ones adds up to 3/8. So the original one is going to be equal to 3/8 plus 1/4. It's going to be equal to 3/8 plus 2/8, which is equal to 5/8. The whole thing adds up to 5/8. All right, let's see what else is next. So that was 28. These are all pretty good. How about something like number 34? 34. Chapter 11, section 2, number 34. This one asks us to consider this series from 1 to infinity of 2 to the n plus 4 to the n all over e to the n. Okay. E is 2.718-ish. So consider the individual terms, right? Remember that for a series to have any chance of converging, it must be true that the individual terms go to 0. So the limit as n goes to infinity of the individual terms, 2 to the n plus 4 to the n all over e to the n, right? We want to figure out what that is. Let's think about that. Well, let's do a comparison. Let's ignore this one for a second and just kind of acknowledge that for each n, for each value of n, it's always true that 2 to the n power, well, each value of n where n is 1 or 2 or 3 or 4, dot, 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 dot. It's always true that 2 to the n plus 4 to the n is going to be bigger than just 4 to the n. Right? Because this is always going to be some positive power of 2, so adding it to this term, well, it's just going to get even bigger. And dividing it by the same thing isn't going to change anything. So 2 to the n plus 4 to the n divided by e to the n is just always going to be bigger than just the 4 to the n divided by e to the n. Okay, so now if we think about the limit of these things, the limit as n goes to infinity of the one on the left, 2 to the n plus 4 to the n all over e to the n, this limit must be greater than the limit as n goes to infinity, of this one. I'm just gonna, since they have the same power, exponential power of n, I'm just gonna rewrite it as 4 over e power of n, right? And we know that if this is bigger than 1, then the whole thing diverges. If it's smaller than 1, then it converges, right? Converges to 0, grows towards 0. If its absolute value is less than 1, it goes to 0, right? So 4 divided by e is definitely greater than 1. And so this whole thing will diverge. Right? It's getting bigger and bigger and bigger and bigger and bigger without bound. It's just growing and growing and growing. Anytime this you have a constant here, there's going to be some constant bigger than 1, and you're raising it to an even power, an exponential power that keeps growing, then the whole thing is going to grow. And this one was the smallest one. So if the smallest one is growing, then that lets me conclude that this one is also divergent. Right? In particular, this is growing toward infinity. So this is also going to grow toward infinity. I don't know what it is, but I know it's getting big. This one is getting infinitely large, so this one, which is bigger, must be getting even more large. It's going toward infinity faster. Okay, but it's definitely not going to 0. And because it's definitely not growing to 0, then I can come back to this guy and go, well, it's going to diverge. So diverges. The sum, right? This is the series now. The sum of this whole series, the series is going to diverge because the individual terms are growing, are diverging. They're not growing towards 0. Because 2 to the n plus 4 to the n divided by e to the n diverges. Good. Remember, the individual terms must grow towards 0 before we even have a chance to think about whether the thing converges. Growing towards 0 is not good enough. So if I had done this and I was able to establish that the individual terms of the series go to 0, well, that's good, but it wouldn't be enough. I wouldn't be able to conclude that it converges, right? Remembering that the harmonic sequence. All right, what else we got? 34. Let's do one of these guys. Determine whether a series converges or diverges by expressing S sub n as a telescoping sum. Telescoping stuff. Okay. How about these are fun. Let's just do 46. Let's look at number 46. So chapter 11, section 2, number 46, and it has one over root n minus 1 over n plus 1, and I have this guy as n goes from 4 to infinity. Okay, so if we just start expanding this out, we will see that a bunch of stuff cancels out. That's what telescoping series are. So if we start by letting n equals to 4, we're going to get 1 over root 4 minus 1 over root 5. That's the first term. And then we get a plus. So these guys are the first when n equals to 4. When n equals to 5, that's the next round. N equals to 5, we'll get 1 over root 5 minus 1 over root 6. That's when n equals to 5. Next, 1 over root 6 minus 1 over root 7. Next, plus, and then we keep going. 1 over root 7 minus 1 over root 8. Okay, so now let's think about, so this would keep going. Let's think about n of these, the partial sum s sub n. So let's say that we wanted to figure out what this was for okay, let's keep going. So this is dot, 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 dot. So let's think about, this goes on forever. So let's think about the partial sum s sub n. S sub n means it stops at n, right? We want to add the first n of these. And unfortunately, it's the same letter there, so we have to come up with a new index, and the most popular index is an I. Okay, and so this is just going to become 1 over root I minus 1 over root I plus 1. Okay, and so doing the same thing, expanding it, now instead of an n we have an I, we're going to get this same thing. We're going to get 1 over root 4 minus 1 over root 5. That's when I equals to 4. Plus, and then when I equals to 5, that's going to be 1 over root 5 minus 1 over root 6. And then plus, I'll do one last one, 1 over root 6 minus 1 over root 7 plus dot, 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 dot. And then the last one is when I is replaced with an n, right? Way, way, way out here. We have 1 over root n minus 1 over root n plus 1. Good. And the one that came right before it was when we had just gotten right before the n was n minus 1. So we would end up with this other one over here that would be 1 over root n minus 1 minus 1 over root n minus 1 plus 1. Right, maybe I should have put that one in color. So this would be n minus 1, and then n minus 1 plus 1. Right? Okay, so then here's where the telescoping part of it comes. A bunch of stuff cancels. Right, so we're looking at s sub n, the sum of the first n of these, stopping at n. Okay, so the minus 1 over root 5 plus 1 over root 5, those guys cancel. And then the minus 1 over root 6 plus root 6, those guys cancel. and then this one's going to cancel with that first one, and so on and so forth. And this one is going to cancel with that one, the one that comes right before it, and this one is going to cancel with this one. And so at the end of the day, the only thing that survives all that cancellation is that first term and the last term. So the only two that were not canceled. And so I can say that S sub n is equal to 1 over root 4 minus 1 over root n plus 1. Okay. 1 over root 4, well, that's just equal to 1/2. So S sub n equals to 1/2 minus 1 over root n plus 1. Okay, and so now if we think about the limit as n goes to infinity of S sub n is equal to the limit as n goes to infinity of 1/2 minus 1 over root n plus 1. And well, this term is not affected by the n. And this term, as n goes to infinity, gets infinitely large, positive. 1 over a number that's getting infinitely large is going to converge toward 0. So this limit goes toward 1/2. So that's what we conclude about this telescoping sequence. The whole thing will converge toward 1/2. Okay, that should give you an example to do something like that. How about these guys? 51 through 56. You get a homework problem there. I love these. How about number 54? Express the number as a ratio of integers. Okay, chapter 11, section 2, number 54. And we had 10.135 bar, right? Which means that that little 35 gets repeated. 10.1, and then we have 35, 35, 35, 35, forever, right? Forever. There are several ways to do this, and there's a couple of alternative ways to the methods presented in this chapter, which are good. But there's also a couple of ways out there that don't really capture the true answer. They just kind of approximate it. And for the purposes of this homework and for your test, when we get around to chapter 11 test, none of those other methods are valid. I want to highlight that. We are doing this, this homework as a way of practicing the ideas, the theorems, the statements that we encountered in this section. So you have to solve it by the methods described in this book and in this section in particular. So just know that when the test comes around, if you find an easier way to do it in some alternate way, I'm not going to be accepting that. Okay, so you have to solve this using the methods of this book, right? The purpose is not to find an answer. The purpose is to practice the methods of this chapter. So, having said that, okay, what are we looking for? We're looking for a fraction which represents this, right? For example, if we had been given 0.33333, right? We know that this, going forever, is really just equal to 1/3, right? When we divide this fraction, we get this, infinite decimal that repeats itself. And that's what we want here. We want some sort of a fraction that will do that for us. Okay, so to do that, the first thing I'm going to do is separate this into two parts. There is the part that does not repeat plus the part that does repeat. And the part that does repeat, I'm going to write it down as 0.0, and then it begins to repeat itself, right? 3, 5, 3, 5, 3, 5, 3, 5, forever, right? So the summation of these two decimals, which is, the same thing as if I had written it this way, 0.1 plus 0.0353535 forever. Okay, so this is just a decimal that terminates, right? So this is the interesting part. How do we find a fraction that turns into this decimal? That's what we want to work with. Okay, so now what I want to do is further separate this in the following way. So I'm going to work with this side, and then we'll come back and glue them all together, right? So let me make some room here. So this is going to be equal to the 10.1. So that's as a mixed number. As a mixed number, it's 10 and 1/10 as a mixed number, which then becomes 101 divided by 10. So 101 divided by 10 is 10.1 plus, and then this is where we insert that fraction, right? We're going to look for some fraction that equals this decimal, and then we'll be able to add them together, right? Okay, so I'm going to go off to the side here and figure out what this is. Let's go off to the side here. Figure out what 0.0353535 forever, what that looks like. Okay, so I'm going to separate this into pieces as well. It's going to be the following. I'm going to write it as 0.035 plus 0.00035 plus 0.0000035. Okay, and you get the pattern now, right? So I can continue this way. 1, 2, 3, 4, 5, 6, 7, then 3, 5, forever. Good. So I'm going to take that idea, right? If I add these up, clearly it's a 0 decimal, and then it always starts with a 0. And then there's nothing but zeros underneath this first 3, so that just adds up to 3. And there's nothing but zeros underneath this 5, so that just gives you a 5. And then there's nothing but zeros underneath this 3, so they just bring you down to 3. And there's nothing but zeros underneath this 5, so that adds up to 5. Right? And so it just keeps going that way. And that's how we generate this infinite decimal. Okay, but I want to write them down this way. So this is equal to 0.035 plus 0.1230, then a 35, plus 0.123450, 1, 2, 3, 4, 5 zeros, then a 35, last one, plus 0.1, 2, 3, 4, 5, 6, 7 zeros, then a 35, right? Plus, dot, 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 keep going that way, right? Okay, so the first thing I'm going to do is I'm going to rewrite each of these as a fraction. So I'm going to rewrite this as 35 over 1,000, because there's 3 decimal places. 35 divided by 1,000 gives you that. Plus, and this will be 35 divided by 1 with 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. Plus 35 with 1 with 1, 2, 3, 4, 5, 6, 7 zeros. Plus 35 over 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Plus, okay, keep going in that pattern, dot, 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 that way. Good. Okay, so now I'm going to rewrite all of these with powers of 10 instead of all those zeros. So that'll be 35 over 10 to the power of 3 plus 35 over 10 to the power of 5 plus 35 over 10 to the power of 7, right? Because that's how many zeros we have. 1, 2, 3, 4, 5 zeros, power of 5. 1, 2, 3, 4, 5, 6, 7 zeros, power of 7. Plus 35 over 10 to the power of 9 plus, okay, well, we see the pattern now. Okay, keep going that way. And now this is a geometric sequence. Notice that to go from this term to this term, right? To go from this term to this term, we always multiply by 1 over 10 to the power of 2. This times 1 over 10 to the power of 2 gives you this term. And this times 1 over 10 to the power of 2 gets you to the next term, and so on and so forth. So we always multiply by the same ratio. You can always get that by dividing as well. This one divided by that one will give you that same result, right? Or this one divided by that one will always give you the same result, right? So this is a geometric sequence. So maybe a little bit of a guessing and checking. Let's write it down and then confirm that it's going to work out. This is going to be a geometric, geo, as n goes from 1 to infinity, where the initial constant, the first one is this one, so that'll be 35 divided by 10 to the power of 3, times r, and that constant term is 1 over, let me make that a little bit bigger, 1 over 10 to the power of 2 to the power of n minus 1. Good. So when n is 1, this is 0, that goes away, that becomes a 1, so we get that first term. When n is 2, we get a 1, so this becomes the power of 1. Multiply them together, we add the exponents, that's how we get this term, and then the rest, right? So this is geometric, where this part is the a. The a in my geometric is 35 over 10 to the power of 3, and this part in there is the r. The r equals to 1 over 10 squared, which is definitely less than 1, so it converges. So, converges. And being that it's a geometric series, it converges to, and remember the formula is a over 1 minus r. So in our case, it converges to 35 over 10 to the power of 3 divided by 1 minus 1 over 10 squared. Okay, simplifying that, we get 35 over 10 to the power of 3 divided by, now 10 squared, that's 100. So this is equal to 100 minus 1 over 100, right? Changing this to 100 over 100. We get 100 minus 1 over 100, or 10 to the power of 2. Go back and rewrite that as 10 to the power of 2, which is 100. Good. Okay, so we have this, which becomes 35 over 10 to the power of 3. That's the fraction in the numerator. And in the denominator, we end up with 99 over 10 to the power of 2. Okay, so we have one giant fraction, where there's a fraction in the numerator, a fraction in the denominator. So we can simplify that by changing it to 35 over 10 to the power of 3 times 10 to the power of 2 over 99, right? Multiplying the numerator times the reciprocal of the denominator. Now, this cancels with most of those, but there's still a 10 in there. And so now if I, that's a 7 and a 5, I guess it can reduce a little bit. So this guy is 7 times 5. And now this 5 can cancel with this 10 to give you a 2. So we have a 2, a 7, and then a 9 and an 11. So that's it. Can't really reduce any further. So we end up with just a 7 surviving in the numerator and 2 times 99 in the denominator. Okay, so let's take that over here. Coming back over here, we see that this is a geometric, right? That's what we did all that work for. We found out that this guy is a geometric series. And this thing converges to 7 divided by 2 times 99. Okay. So we simplify this. So this is going to be 7 over 198. Common denominator, well, just be the easiest thing. Well, that's fine. We have a 10, which is 2 times 5. That's equal to 10. And then we had the 198. Find its prime factorization. Well, that was the 2 times the 99, which is going to be 2 times 3 squared times 11. Right? So we take the 2, the 3, the 5, and the 11. And we use the biggest exponents available. So that'll be 1, 1, 2, and 1. And that product will be the least common multiple. Good. Or another way to look at it is that the prime factorization is this guy, and this is the least common multiple. So the only thing that it's missing is a 5. So we multiply this one by 5 over 5, right? Because the 198 has the 11, and it has the 3 squared, and it has a 2. So it's missing a 5. And now the 10, that's 2 and 5, 2 and 5. It's missing a 9, and it's missing an 11. Right, so multiply by 99. All right, so then this becomes 9999 divided by 990 plus 35 divided by 990. So we end up with 10,034. Oh wait, yeah, 10,034 divided by 990, which can easily be reduced, of course, because it ends in an even number. So we can divide the numerator by 2, divide the denominator by 2, and we end up with 10,034 divided by 2, end up with 5017 divided by 490. .990 divided by 2, which gives you 495. Okay, reducing your fraction is not, you're not going to be penalized for not properly reducing it on the test, so don't worry about that. Any one of these would have worked, right? So this is our answer. This is the result that gives you the 10.1353535 forever, right? Let's check it. Let's go to our calculator. And there we go. And of course, my calculator is just doing a little rounding here, but you can see the beginnings of it. 10.1353535. And then the calculator does gives up and does a little rounding there. I think it might be part of the settings, how many decimal places before it, gives up. But it is our result. Right, so like I said, you didn't have to reduce it if you just stopped here. 10,034 divided by 990. You get the same result, and I'm fine with that. Or even if you got another one, when you came over here and you wanted to add these fractions, you might have come up with an easier, faster way to do it. That's fine. You don't have to find the least common multiple. You just have to find a common multiple, and you would have gotten your results. And also over here, when I was simplifying this, I did some canceling and reducing that maybe you don't do, and that's okay. There isn't a unique answer, and I'm not even sure if this might reduce some more, right? I'd have to really think about it. Maybe they're both divisible by some number as well, right? Clearly not 2, clearly not 5. But who knows? Maybe they're both divisible by 7, or maybe they're both divisible by 19. I don't know. So don't worry about reducing it any further. We just want to get to the point where we combine them and we get one happy fraction, such that when we divide that fraction, when we get that that ratio, that it gives us the decimal, the repeating decimal that we were asked to find. Okay, so the key to these is always going to be to rewrite it into two pieces. The part that repeats, the part that doesn't repeat. The part that doesn't repeat is just going to be some easy thing to work with. The part that does repeat, we want to use this. We want to use the knowledge of geometric sequences, geometric series, to establish that it's a geometric series, figure out what the value of A is, what the value of R is, confirm that the value of R is less than 1, and then we use our little formula for the sum of an infinite series, infinite geometric series, to come up with a fraction. See this part, 7 divided by 198. That will generate just the decimal part, just this part right here. Let's check that. 7 divided by 198. See, it just gives you the 0.0353535, repeats, and then all we have to do is figure out a way to add the 10.1 to this, as we did over here, and then that'll lead to our result. Okay, I think that should give you a pretty good sense of all the various questions for you to figure out your homework. So I'll stop there for now.